Welcome to week 6 in review. Today we're going to cover two main topics, reachability and also linear state feedback. And as we've seen in class, these two things are remarkably related. So there's two basic questions we need to consider. Given an LTI system in discrete time or continuous time, for convenience here I'll just write the discrete time version. X of k plus 1 is equal to a x of k plus b u of k. Is there an input sequence u? So this means from k equals 0 to some final time t minus 1 that takes the system from some initial state, and I should say from any initial state, let's call this x of 0, to any desired final state, x final. And we answer this question by basically unwrapping the recursion and finding that x of k plus 1, or let me write it directly as x of at time n, is equal to a to the n times x of 0 plus the sum from k equals 0 to n minus 1 of a to the n minus 1 minus k, the u of k, which we can also write as a to the n x of 0 plus this matrix a to the n minus 1b. I write this because these are columns, to remind us that these are columns. So this is an n by 1 column times the vector of all the u's. U of 0, u of 1, all the way up to u of n minus 1. And what this tells us is that this is the key thing that we need to understand. So what we did is we let R equal this matrix, an minus 1b down to b. And note that there's no index on R, but that's because, so really this is equal to Rn, but we denote this as R. N here is the dimension of X, and so similarly A is an n by n matrix, B is an n by 1 matrix, etc. So this is called the reachability matrix. And we saw in class that the answer to this question is yes, as long as R has full rank. Which is equivalent, since R is a square matrix, to the determinant of R being different from 0. So this led to the following definition. The pair AB is called reachable if the matrix R has full rank. And note that really this is a property of both A and B together. The next question we considered moves us on to linear state feedback. Well, before I get to that, I should note that we showed this for discrete time systems, but as explained in chapter 6 of the book, exactly the same relationship holds for continuous time, linear time invariant system. So the reasoning is a little bit more complicated because we need to do integrals rather than just iterate the recursion. Okay, so the next important question concerns linear state feedback. So let's move to continuous time. Of course, everything holds for discrete time as well. So suppose we have x dot equals ax plus bu, and we want u to be a feedback policy, which means that it's some function of the state. But moreover, we want f to be a linear function. Well, if f of x is a linear function, then it has to be something like k1 x1 plus k2 x2 plus kn xn. And for tradition's sake, this always appears as a minus sign there. And we can always write this, therefore, as u is equal to minus kx, where k is a 1 by n vector, and x is, as usual, an n by 1 vector. So the question, Q2, question of linear state feedback, is, can we choose a matrix K so that the system is stable? And of course, this is most interesting when the autonomous system is unstable. Because if the autonomous system is stable, so recall the autonomous system is just x dot equals ax. If this is already stable, then we can just choose k equal to 0, and so the answer is yes, but it's not very interesting. Okay, so this is the problem. So let's see what the closed loop dynamics are. So in other words, if we plug in u is equal to minus kx, we get x dot is equal to ax plus b times minus kx, which is equal to a minus bk times x. So basically, Q2 is really asking, can we find the 1 by n matrix, a 1 by n matrix, K, so that a minus bk is stable? And of course, we've analyzed what that means. So note that on the surface this could be quite a difficult question because we'd have to compute eigenvalues of a minus bk, and we'd have to express those eigenvalues as functions of k and see if we can find something that stabilizes, that puts all the eigenvalues on the left-half plane. So that could potentially be complicated. It could lead to nonlinear equations. So a key simplifying factor is something called reachable canonical form. And the pair A and B is called, or is said to be in reachable canonical form if B has the form 1 with all zeros, and A has this special form, minus an minus 1, minus an minus 2, all the way down to minus a0, so note A is an n by n matrix, and then 1s below the diagonal. So there's zeros everywhere else. So there's 1s on the just below the main diagonal. And the key thing that we proved in class, which I won't repeat here, we proved this by induction, that the characteristic polynomial of A is revealed by its coefficients. So the same way that an upper triangular matrix, or even more special, a Jordan canonical form matrix, reveals the eigenvalues, the reachable canonical form, a matrix that's a part of a pair that's in reachable canonical form, reveals its characteristic polynomial. So specifically, what we proved is that the determinant of lambda I minus A is equal to lambda to the n plus, note the sign flip, an minus 1 lambda to the n minus 1 plus all the way down to a0. So for example, if I give you the matrix A is equal to 3, 5, minus 6, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and I want to know its characteristic polynomial, well, we could compute the determinant of this 4x4 matrix, but that could be painful. But using the proof that we had in class, the induction proof, and the result above, we know that this is equal to lambda to the 4, because this is a 4x4 matrix, minus, note the sign flip, 3 to the lambda cubed minus 5 lambda squared plus 6 lambda minus 1. And you can check this to see that in fact this is true. So what is so great about reachable canonical form? With A and B as written, A minus BK is now equal to the special matrix minus AN minus 1 minus K1 minus AN minus 2 minus K2 all the way down to minus A0 minus Kn. In other words, A minus BK is already in reachable canonical form. So in other words, if the pair A, B is in reachable canonical form, then we can easily compute determinant of lambda I minus A minus BK, which is sometimes called the closed loop system matrix. A is sometimes called the open loop system matrix. So, in other words, the determinant here, the characteristic polynomial in closed loop is lambda to the n plus, again, not the sign flip, an minus 1 plus k1, lambda to the n minus 1, all the way down to a0 plus kn. So what do we see here? We see that by adjusting by proper choice of k1 to kn, we can make the determinant of lambda I minus a minus bk be any polynomial we like. In particular, we can make it be a polynomial that has roots on the left-hand plane. We can choose k1 to kn so that all the roots of this characteristic polynomial are in the what's called the open left half plane, i.e. the real part of all the roots is strictly less than 0, and hence the system x dot is equal to a minus bk. X is then stable. And how do we do this? Well, one way is we pick roots in the open left half plane. Say, let's just do this completely generically. Pick roots R1 to Rn with the real part of Ri strictly less than 0, and then multiply this out. Lambda minus R1 times lambda minus R2 times lambda minus Rn. This is now going to be some degree n polynomial. Lambda to the n plus bn minus 1, lambda to the n minus 1, all the way down to b0. And then equate coefficients. In other words, we have the product of lambda minus Ri equals lambda to the n plus b to the n minus 1, lambda to the n minus 1, all the way down to b0. And this is equal to, we set it equal to, lambda to the n minus 1 plus an minus 1 plus k1, lambda to the n minus 1, all the way down to a0 plus kn. And equating the coefficients means the n minus 1 is equal to an minus 1 plus k1, which means that k1 is equal to bn minus 1 minus an minus 1, and all the way down to b0 is equal to a0 plus kn, which means that kn is equal to b0 minus a0. And with this choice of coefficients, we have the roots that we want. So choosing k1 to kn in this way puts the eigenvalues of a minus bk at the chosen points, r1 to rn. So what we saw last time, that we can choose a change of coordinates, z is equal to tx, that puts a system into reachable canonical form exactly when that matrix R, the reachability matrix that we saw from question 1 above, has full rank. So this has the same exact answer from above. And we'll be exploring this more in this coming week.